Hello everybody, I'm back again. We're going to do some more electrochemistry. Last time we made a link between the board falling down. We made a link between the standard cell potential, standard conditions, with some of the thermodynamic variables, namely the equilibrium constant K and standard delta G. We made a nice relationship between them. We were able to show links between these. We were able to talk about spontaneity in light of E0 cell, as well as comparing Q to K and so forth. So today I'm going to first start out with working a problem, and then we'll expand this description to include other thermodynamic variables, including under non-standard conditions, which is important. So let's do an example. Let's say we have the conditions, it's 25 degrees Celsius, and we're working under standard conditions, standard state conditions, right? So meaning the molarities in this problem are all going to be 1 molar starting out. So let's go to your table and find two reduction potentials where we have copper and 1 electron going to copper solid. And you'll see on the table it's 0.52 volts. For that, the table's all written as reductions. And then let's look at silver plus 1 electron being reduced to silver and find that, and it should be above it on the table, slightly larger value, 0.80 volts. Let's say what we wanted to do was the following redox reaction to make a battery. Let's say we wanted to do copper plus 1 plus silver going to Ag plus 1 plus copper. Would that be a good idea to be spontaneous as written under standard conditions? When I'm looking at this is the anode, the silver system, and the copper is the cathode, right? So a little quick calculation after we tabulate this is E0 cell is the voltage of the cathode minus, so the cathode is 0.52 volts minus the anode 0.80 volts, and that's equal to a negative 0.28 volts, right? So that doesn't look too good if you want to have a spontaneous cell under standard conditions that would not want to go to the right spontaneously. If we wanted to put it in terms of K, the equilibrium constant, let's do that really quick and rationalize it from that perspective. We have the relationship we derived last time, E0 cell is equal to, I'll put it in the log 10 form. You're welcome to put it in the natural log form if you like. 0.0592 volts over N log, and that's log base 10 of what? K, right? So you can solve that out for K. K is going to be equal to, let's see here, we'll just cross multiply. It's going to be 10 N E0 cell divided by 0.0592 volts. Here, N is equal to what? N is equal to 1, right? So that's just a 1 in there. So we're just going to have the ratio of the cell potential to this constant 0.0592 volts. So that's equal to 10 to the, let's see here, negative 0.28 over 0.0592. And what that comes out to be is to 2 sig figs 1.9 times 10 to the minus 5. 1.9 times 10 to the minus 5. Think about this, is that under standard conditions, Q, the reaction quotient, is equal to silver plus 1 ion, concentration and molarity, over copper plus 1 ion, right? And that's precisely equal to 1 because under standard conditions, that's 1 molar divided by 1 molar, giving you 1. Meaning Q is what? It's far greater than K. K, you may not think Q is a big number, it's 1, but it's a lot bigger than 10 to the minus 5, right? So what that tells me is what? When Q is greater than K, the reaction doesn't want to head right. it actually wants to head to the left, which reconfirms it's spontaneously not wanting to go this way to products, it's actually wanting to go the other way to reactants. So let's flip the process around and let's do this. Let's leave everything up there except, let's say, we said, well, that's not going to work, so let's do it the way nature wants to kind of go. Let's make the reaction this. Silver plus 1, we'll call this reaction 2, if you will, plus copper solid going to copper plus 1 plus silver solid, right? In that case, the cathode and the anode have switched. In this case, the silver now is the cathode, and the copper reaction is the anode, right? It's being oxidized. The copper's being oxidized to copper plus 1. So what we do is now E naught cell is 0.80 cathode minus anode 0.52 volts, and that's equal to a positive 0.28 volts. I'm just putting a positive sign there for emphasis. You don't need it mathematically, just for emphasis. So doing that, first place, that tells me it is spontaneous to the right. As written, this system will work under standard conditions if silver is being reduced to silver plus 1 to silver solid, and copper solid is being oxidized to copper plus 1. To calculate the equilibrium constant for it, we do the same thing we did before, except now we're going to have, when we solve for K, 0.0592. I always get the numbers mixed up here. Volts divided by what? I got that backwards. It's going to be the E naught cell in the top, right? So it's a positive 0.28 volts divided by 0.0592 volts. There you go. I knew something was wrong there. It has to be a positive number. It's going to be 5.4 times 10 to the 4, right? No units on K. That's a lot bigger than 1, meaning that in the, Q under standard conditions is still equal to 1, right? And that's going to be now far less than K, right? K is on the order of 10 to the 4, right? Meaning, by that interpretation, it has the same interpretation just from a different vantage point. E cell positive, we want to go to the right. Q less than K, we want to go to the right. Meaning, in terms of spontaneity to the right, this will work, reaction 2 versus the reaction type initially proposed. We'll call it reaction 1, where it was the opposite. So these are ways that you can link together thermodynamic ideas with electrochemistry, kind of develop a whole cohesiveness for it. I'll let you look at this board a little bit. So one of the things I'm seeing here is that naturally in this conversation I'm evoking Q. I've kind of tied in the idea of Q to this thing, off to the side, if you will. That's the reaction quotient. Remember the relationship between Q and K. K describes the equilibrium condition, right? That's when you have the reactions to the forward direction have the same rate as in the reverse direction. That's the equilibrium condition, dynamic equilibrium. They can be equal. Q can be equal to K at equilibrium. Q is any point along the coordinate. The reactions do not have to have equal rate. In general, they won't, right? You're going in a preferred direction in nature, typically, unless you're at the equilibrium condition. And then we have delta G, which is a statement of the free energy changes that occur in this process under any conditions. It doesn't have to be that one-trick pony of standard conditions that we basically use for a reference position. We use that referentially. We'll say, okay, at 25 degrees Celsius, we have these conditions, 1 molar concentrations, 1 atmosphere partial pressures, and so forth. It's just a reference point for people to have a common language to think about how they're moving relative to some other point. So let's develop a relationship, and this starts roughly page end of 14 going into 15, about cell potentials under non-standard conditions. So let's do this out. The derivation is really, it's just putting two equations together. but ties together two different things that we've talked about at different points, so let's write that. So we had earlier on a relationship that delta G naught is equal to negative NF E naught cell. So we did this through the idea of work. These are both statements of both sides of this equation are the maximum work you can get reversibly out of an electrochemical cell, with the caveat of its constant temperature and pressure, which we'll take that as typical lab conditions. We're under atmospheric pressure overall, and we're keeping the lab relatively constant temperature. We'll just say room temperature is about 25 degrees Celsius. So, that's a good approximation. Working under relatively constant T and P, unless you don't have good air regulation in your room, that could be a problem. So we have that relationship, and earlier in the course we have the relationship delta G is equal to delta G naught plus RT. I'll put this in the natural log form, ln of Q. We derived that out, or we stated this earlier in the course. We have that, right? So what you can do is use these two equations, together. Use these two equations to show this. I'll leave that for you. That's simple algebra. It's actually worked out in notes, but try to do that algebraically for yourself and get it to the form of this. Get it to the form of, I'll write it like this initially, E cell. And that's not E naught cell, that's any old conditions cell potential, right? Doesn't have to be standard, is equal to E naught cell minus RTNF ln of Q. Get to that form. I'm going to work it. It seems people like to use log 10 more, and you can totally work this in the ln form. I'm going to put this in the form of a number form for plugging into calculations. E cell is equal to E naught cell, standard potential, minus, and I'll use the log 10 form, 0.0592 volts over N. Again, and we need that, and we'll put this in the log Q form. This is log base 10. It seems people like that better. If you do not like this form, then put in the RTF value we developed for the natural log function. You can use either one you want. So this is a nice relationship because we can readily calculate E naught cell, provided we know cell composition. We're no longer limited to things being, for example, 1 molar exactly. They could be any value. They're not limited if we have gases in there to being 1 atm partial pressure. N comes from the the balanced redox reaction. Look at the number of electrons transferred per reaction unit, and we can figure out the cell potential from that for any condition. And this is what you'll see when you're making a real battery, let's say. Over time, sometimes quickly, the composition's changing and you see the voltage changing as the composition changes. So you could get information on how much electricity you basically can get out through this. It's further calculation from your battery at a particular point of its reaction progress, and you can use that information backwards to tell what your composition of your system is, provided the chemical species in it. So let's use this equation to. This is written on page 15 of your notes, and I'll do a skill builder that's in there. Once I set it up, if you want to try it on your own first, and then finish out the video, you can stop in a few seconds when I write down the conditions, or just look at the skill builder and try it on your own. So we want to calculate E cell. We're at 25 degrees Celsius, I'll say. We'll put that we can use this equation. Usually on the test I put that in there. We'll say this, we have the anode is going to be zinc 2 plus zinc, meaning we have zinc, maybe it's zinc sulfate, in the presence of a zinc electrode, solid electrode. And for this, the composition of the concentration of the zinc 2 plus is not 1 molar now, it's 0.25 molar. As soon as I see that, it means I'm not standard conditions, right? I'm not standard, it's not 1 molar. And the cathode is going to be similar. It's going to be copper 2 plus and copper solid. And the composition of that is the copper is going to be 0.15 molar. And so again, this would be like a copper sulfate solution for your cathode with a copper rod or a little sheet of plate of metal in there attached to it. So that's what we to look like. I'm going to use this form of the equation. You can use that. Some of the things we'll calculate first. We need to get E naught cell. So this would be like in fantasy world. What if we were under standard conditions? We use the table. So look up these values. The reaction that we're doing, I always like to write this out, is we're doing copper 2 plus 2 electrons going to copper solid, and then we're doing on the other side zinc going to zinc 2 plus 2 electrons, meaning N is equal to 2, and the overall reaction looks like this. Copper 2 plus zinc goes to copper solid plus zinc 2 plus. So the cathode, you look it up on the table, is 0.34 volts minus, and I always put a little bracket here, minus 0.76 volts. That's for the zinc reduction. Remember, they're written on the table as reductions. You're not going to find it written like that for the zinc. It's going to be written the opposite way. The negative sign in the front builds in for the fact of you having to kind of flip it, but you don't physically flip it. Take it directly off the table as it is. That table has this form, cathode minus anodes, building in that flip, if you will. This ends up being a positive, which sounds like a 1.10. I'll put a positive here just to make emphasis. 1.10 volts. We're pretty much there, right? Off to the side, let's do Q. Q is going to be equal to zinc 2 plus over copper 2 plus, which is going to be, let's put it in here, zinc 0.25 molar over copper 0.15 molar. I don't need the molar in there to cancel, and it's dimensionless by definition. That should be 1.67. 1.67, right? So we have that. At this point, all we have to do is plug in here. E cell is equal to 1.10 volts minus 0.0592 volts. That carries the units, volts and volts. And then we just put the number, what do we have here? We have 2 here, right? We have 2. And then we have log of 1.67. That's Q. It's no longer 1. It's Q is not under standard conditions. So we do it out. I don't have the calculator. I'll just look at my answer. Verify that for this you get 1.09 volts, and you can put it positive if you want to make emphasis, meaning the reaction over here is spontaneous to the right with this concentration scheme, which is not standard. So that's great. That's good information. Now you could play with this and potentially get a concentration profile that might override this number. It may be unrealistic, like you may physically not be able to get a concentration of zinc or copper to match that number, but you could theorize what that would be. Set this equal to 0 and figure out what that ratio would have to be, and then enhance it a little bit, to push you in the other direction, and you can find it. Again, it may not be a realistic concentration ratio because this has to be a pretty big subtractive number overall to make this become negative, but we can always theorize like what it should be. You just may not be able to do it. And so this is super practical. This tells you under real conditions if you'll go spontaneously to the right or not. For a real battery, you could apply this to biological systems for things like the ETS, the electron transport system, and other. We have a lot of redox chemistry in the body, and not animal and human body. I mean, you have the electron transport system. You have, for example, cell potentials. You have potentials associated with separations of specific ions across batteries. The charge carrier often is electrons, but in biological systems, the charge carrier can also be specific ions like sodium ion and potassium ions and so forth. They have those ions emit an electric field. They are conductors of electrical energy and so forth. They don't have to be electrons to be a part of having an electrochemical system. So you have things that in the body that you'll use if you go on far enough in physiology and biophysics and subjects like that. all this stuff comes into play, albeit it's far more nuanced. It's actually a lot more complicated. So also, let me say this, we're pretty much finished with the galvanic part of this, the voltaic part, the spontaneous cells. We have shown that some cells are non-spontaneous, and we'll address what utility those have next. I mean, some non-spontaneous reactions are useless, but others, like electroplating gold or silver, are hugely beneficial to humans in terms of industry and so forth. So the last section of this will be on electrolysis, which is basically driving a non-spontaneous process by putting in energy or putting in work into the system, which we can do all day. So we'll talk about that next. We'll do some practical calculations. That will wrap up electrochemistry, and then after that we will move on to nuclear chemistry, if you want to consider that. It has a lot of physics ideas in it as well, but it's a great subject because it will take us back to the nucleus and how elements, for example, can change to other elements in fusion and fission processes. We'll study the difference between fusion and fission. We'll study some of the basic nuclear types of decay that can occur. We'll study reactive decay mechanisms and so forth. So I think it's a really good chapter. So on that note, we're just about done with this chapter and moving on to nuclear chemistry next. Take care.